Hey guys, welcome to part 3 of my Z80 computer build. In part 1 I explained about the CPU and the basic build of this project. Part 2 dealt with the RAM and ROM memories and the memory mapping and how they work. And this is part 3 where I've combined the two together, the CPU and the ROMs. And this is what this part will deal with, just the minimum setup. Now I have a bit of a cold, so I will try to do this without coughing or sneezing or anything in between. But let's just get started with it. We have a minimum system right now. And you can see here from the user manual what is the description of a minimum system. We have the CPU, we have a clock, we have the ROM chip, and we have a dedicated input-output chip, which we don't have on the circuit, but we do have a board with the LEDs which just tap in directly to the address bus and the data bus, and they provide us with output so that we can monitor everything that happens. Let's just review the breadboard real quickly. Right here in the middle you can see the CPU itself. It's connected to the address bus and it's connected to the data bus. On this part here we have the ROM chip and we have the RAM chip. Again, both are connected to the address bus and the data bus. And right here we have the memory mapping circuit, which will decide which memory we're talking to. Over here we have a clock, which is a 555, and it operates at about 1.3 Hertz, and that means that it's basically just doing an instruction about once per second. At this point it's worth mentioning that the CPU itself, for correct functionality, it needs to have at least a few kilohertz because there are internal timing mechanisms in there. But the Z80 CPU is a robust one, and it can handle even such slow speeds when we're just dealing with a few commands, a few instructions. And obviously with more instructions you want to have higher speed, since you're not going to wait for each one of the bytes to load and so on. Other than that, we can see here I have just a 5-volt regulator. Right here, pull down resistors, which I just made nicely with the plastic from a 40-pin male connector. Again here, the LEDs, LED for the clock, LEDs that will indicate either we're using the ROM or the RAM. Right here we have the outputs. Let me just center that. That's it. We have the outputs for the address bus, starting from A0, and the data bus starting from D0. And that's about it. That's our minimum setup. When you're looking at the LEDs for the ROM and the RAM, again remember that they are on a high, on an active high. So that means that when they are low, we're communicating with one of the chips. When they are high, they are disabled. The ROM chip, I've partitioned it right here. This is the ROM chip. I've partitioned it since it's a 2 megabyte chip and I'm not using all the pins. Right here we can see the partition table. So the ROM chip, it will have addresses from A0 to A17. Since we're only using A0 to A14, 15 bits and 16 bit is used for the memory mapping. That means that we have a lot of memory left over, and I've partitioned it, so I will manually set one of those pins, 15, 16 or 17 to high, and then I can select different programs that will load. So for example, when all 3 pins are on low, we're just starting to read from address 0 on the ROM chip. When we have a pin 15 on high and 16, 17 on low, we're starting to read from address 8000. The CPU, it doesn't know that this happens. The CPU just treats it as starting from address 0, but we are manually placing a jumper on the ROM chip, and that means that as far as the CPU is concerned, it starts from address 0. As far as the ROM chip is concerned, we're starting from address 8000 or 10,000, or the way we partition it. Let's just get started with the first set of instructions that I'm going to demonstrate. And let me just fold this page here so that we'll have it all nicely. I'm going to turn it on, and right now you can see that it's turned on, and we're starting to count. What this instruction will do, it's a simple single instruction, which means jump to 0. So right now we are at address 3, we still have a nope inside. Address 4, we will read a value, there we go, C3. The following values at address 5 and address 6 will be both 0, since we're jumping to address 0. And then the CPU will jump back to address 0 and start the loop again. So right now it jumped, it started again from address 0, but we're seeing these other addresses come up here. We have 7 and we have 8 here, and this is the first thing that I need to explain so that you can understand the rest of the examples that I'm going to show you, just so that you can follow them. What you're seeing is the refresh addresses that come up. There is a refresh register, register R in the CPU, which tracks the refresh addresses. And if we look at the timing cycles, so again, the Z80 user manual, it's your best friend for these things. All the information is in there. We can see the machine cycle. And this is something that I already talked about a bit on part 1. But right here we can see that in between the cycles we will get a refresh address coming up on the address bus. This is not relevant to us. This is only relevant when you're using dynamic memories. To the programmer itself, so the guy that actually programs this, if he was sitting in front of a full working system, then he wouldn't be aware that these addresses come up on the address bus, and they are completely transparent to what the code actually does. But to follow it, in this single instruction code that we're seeing here, what will happen is the CPU will start up normally, so it will start at address 0, it will have an instruction fetch, and then it will also provide a refresh address on the address bus. It will continue doing so until it reaches address 6, where it's going to actually carry out the jump. And at address 6, the instruction fetch cycle is going to start again from 0, and the refresh state is going to continue counting 7, and then 8, and 9, and A, B, C. And again, this repeats, and it's a single byte register, which can reach, I think, up to 7F, and then it will reset itself. But that is what we're seeing right here. So if you are expecting, like this program, you would say, okay, I reach address 6, and it should just jump back and not continue counting towards all of these values. Then what you're seeing is correct functionality, and you're just seeing the refresh addresses come up on the address bus. Again, they have nothing to do with us, since we're using static memories, but they are used for dynamic memories, and they don't have any influence on what we're doing right here. So this was the first instruction. Again, it will start, it will reach address 4, it will read this instruction, you can see it right here, then it will read the value that it actually needs to jump to, and it will carry out the jump, and that's it. That was the first instruction. The CPU is carrying it out as it should, and everything seems to be working fine. So the next example that we're going to look at, I'm just going to turn it off. And right now I'm going to select a different partition, so the next partition. So what I'm doing is I'm taking a pin which just comes from my 5 volt supply. I'm setting the pin number 15 to high, and that means that we're starting from address 8000. The next example that we're going to look at, and I'll just fold it again, is this one, which is again a jump, but this time it's a sort of different jump. Here, first of all, we are loading both values, registers H and L, with a value that we want to jump to, and then only then we are jumping to whatever address sits in register HL. So right now we're reading address 3 again, and we're reading address 4 right now, which is the load command. Load the value 00 into H. Then we have the load value right here to register L. We are loading the value 4, which are the lower bytes. And here we have the jump, and we're jumping back to address 4. So we're basically starting up again. We're just putting the value 0 in H, the value 4 in L, and then jumping back to address 4. This is what we're seeing right now. And again, we're seeing the refresh addresses come in between. Sorry for that. And everything seems to be working okay. Right here, we can see that we are communicating with the ROM each time. The RAM, unless it comes on a refresh address, the RAM is pretty much disabled all the time. But we're gonna move on to the next set of instructions, which is a bit more interesting than this, and it also touches just a little bit on what will come up in part 4 of this series, which is dealing with input-output. I'm just gonna turn it off again and again. I'm just setting my partition 1 higher so that we are starting to read this time from address 10,000, and I'm gonna turn it on. This one will take a bit of time. So we're going to first cover the basic commands that go through this. Let me just put this a bit so that we can see the whole page. Can we? I think we're okay. So we're at address 3 right now. We're loading the value 11 into register HL. This time we're dealing with 16-bit instructions. Up until now we dealt with only 8-bit instructions. And we're loading the value 11 into register HL. We're loading the value 8000 into register DE. We're loading the value 10 into register BC. This is all happening here. We're not seeing the end result yet, which makes this example important, but we're going to get there. Once we're going to get right here, we're going to get to the LDIR command. Then what this program actually does is it will take a string. The length of the string starts from address 11, and its length is 10, so it will be up to 1A, and it will copy the whole length of the string from this memory location, which we start at register HL, and we copy it to the RAM memory, which starts at address 8000. So you can see here that every time it will take a value, it will then switch to the RAM memory, like right now, and it will write this value, and it goes through this loop until it will load all of this set of instructions right here. It will load it to the RAM. Once it has loaded it through the RAM, right now it's just going through the loop, loading it in. Once it loaded it and it finished with this instruction, we call address 8000, so we're addressing the RAM, and from there on the program will start just running from the RAM again in a loop where we're loading value 2 into register A. Again, 8-bit commands. These are 16-bit commands. Here we have 8-bit commands. We're loading the value 1 into register B. We're adding A and B, and then we're also outputting the whatever value sits in register A. We're outputting it to whatever device that is connected to register F. And that is the important bit of this demonstration. So we're gonna wait a moment until it finished loading everything. Right now it's at address 5. So at address 5 we can see the add command. It still needs to load all these 5 addresses. So we're going to give it a bit more time. Once it's loaded it, then again it will start at address 8000. It will run through this set of instructions, and at the end it will jump to address 8004, which is the add instruction, and it will continue adding a 1 to a 2, outputting the result, jumping again to the add, and again adding, and so it increments it and it outputs the result to whatever device will be connected at address F. That's what it does. So in this example we are using both the ROM and the RAM, and we're using this entire setup here. We've loaded the program from the ROM into the RAM, and then we're just running everything from the RAM. We will still see that the CPU tries to communicate with both the RAM and the ROM. Again, there are the refresh addresses in there, but basically to the programmer that will just sit in front of this system, as far as he is concerned, we're running everything from the RAM itself. At a certain point you will see here, once the call instruction is executed, everything will go high and the computer will just start reading everything from the RAM, which will happen pretty soon. And that's there we go. So it's loaded it into the RAM. Right now we're starting at address 0 of the RAM memory, and we have the load command. Next, at address 1 we're loading the value 2 into register A, and then it will go to address 3. We're just loading the instruction for load B. Address 4, sorry that we're already at address 5 right now, we're adding. This is the address for the output device, and right now you can see the output. The device sits on address F. On the lower bits we will see the address of the device. On the higher bits we will see the result. The first loop has been executed, so we had the value 3. You will see it here, and you will also see it on the higher 8 bits. So right now we will come to this instruction. Here we're setting the instruction out to F, and we have the value 4 at device F, and the next value will be value 5, since we're continuing to add 1 to the initial result that sat in register A. So we're dealing basically with an input-output. That would mean that if we had a very basic device, maybe just a small speaker or a buzzer, sorry, that is connected to the address bus on address F. Each time that we would address F, regardless of the output here, we will just set it hardwired, we will get a tone from the speaker. And nothing is addressed on the ROM and the RAM. Once it gives an output, you will see that they will both be disabled. Like right here, they're both disabled, they're both in a high Z state. And you can see we already reached 6. So that's how it's continuing to count the loop. And basically that's how our system works. So that's it. We have our minimum setup right here. We're using the CPU, we're using the ROM, the RAM, memory mapping. We can switch between the two. By the way, in a good program, this is just a random set of instructions that I made up. We can't really call it a program, but definitely this part right here can be treated as a function. So we can say that this is a single function that we made, and it's a valid one. It copies a string from point A to point B in the memory. But once it calls this address, and I've mentioned it also in part 2, we're starting to read the program from the RAM, and it will run it. Once the program, maybe if it doesn't have this jump that just keeps it in a loop, we will need something that will tell the CPU, okay, the program in the RAM has finished and we need to return back to the ROM. And at the end here there will be a return command which will return it to some address in the ROM where it can go further handling the system. So yeah, that's about it. And again, if you're looking for information about this project, just check out the description and you will find there everything that you need. I hope that I covered everything that I had planned for this video, and if not, then feel free to leave a comment or ask, and if I can, then I will give you an answer. Hope you liked it. If you haven't subscribed yet, then consider doing so. It encourages me to make more videos. Other than that, thank you for watching, and I'll see you next time.